Good morning, everyone. I hope you had a good spring break. In this video, we're going to be starting our new unit called thermochemistry, which is the chemistry of heat. Now, the reason why we're learning about heat is a form of energy. Now, energy is the ability to do work or produce heat. So to do work or produce heat. Now, when we talk about the doing work, that's like pushing a desk, moving your arm. This is normally what you're going to learn in physics class. The producing heat part, this is what you're going to really focus on in chemistry. You touch on it slightly in physics, but for the most part, this is what we're going to talk about in chemistry. And heat, so this word thermo means heat. And so thermochemistry is the chemistry of heat. And heat or energy, right, which we'll just talk about those as interchangeable words, is used in chemistry to do a couple of things. The first thing it's used is to break or form intermolecular forces. And you should recognize that word because it's a vocabulary word from first semester. But in case you do not remember, that is a force that is between molecules. So between neighboring molecules. So for example, if I had two water molecules, let's say I have two oxygens and two hydrogens, there could be an attraction between the neighboring molecule, and that force between neighbors is an intermolecular force, or it's abbreviated as IMF. Now, when you break or form, so either break existing forces or make new ones, these are going to result in physical changes. Okay, these are going to be physical changes because you're just breaking the molecules or the forces between the molecules, not anything of the actual molecule. And so these could be, any sort of phase change. So for example, melting is breaking the forces between solids while loosening them to go from a solid to a liquid. Boiling, being able to go from a gas to, or from a liquid to a gas, or the reverse, condensation, or freezing, right? All of these are phase changes. And so when we look at these phase changes, they are all breaking these intermolecular forces, or the forces between molecules. And we'll talk about these more in detail in a later video. They can also break the other type of force, which is our intramolecular forces. Now, you're going to have to pay attention here because the main difference between these two is this is inter, this is intra. Now, intramolecular forces are within the molecule or inside the molecule. So, for example, when I look at water a little closer and we have hydrogen or two hydrogens attached to one oxygen. Remember, this line represents a covalent bond. And some compounds like sodium and chlorine, because they're positive and negative, have an ionic bond. And all of those are intramolecular forces. They're inside the molecule. Now, breaking existing bonds, covalent bonds or ionic bonds, and forming new ones results in chemical changes. Now, remember, all chemical changes are also chemical reactions, which I abbreviate the word reactions as RX and S. frequently, so you're going to need to know that abbreviation. And so an example would be breaking the bonds between water to form oxygen and hydrogen gas again. Forming sodium chloride through mixing solid sodium with chlorine gas. All of those are chemical reactions. Now, we're going to dive into this one a little more deeply. This one, when you look at them, number 2, breaking intramolecular forces, this is the one that requires the most energy because those covalent bonds and ionic bonds are going to be much stronger than these intermolecular forces. So that is why we're going to dive into it a little bit more right now. Also, they're about chemical reactions, which is what we're normally used to talking about. Now, there are 2 types of chemical reactions. Now, I know we've talked about double replacement and single replacement and combustion and all of that. Those are the types of reactions based on how they are reacting, but these 2 classifications are in terms of heat. So, and you should have learned them in physical science. The first one is endothermic, and the second one is exothermic. Now, when we look at these 2 types of graphs, or 2 types of reactions, and in an endothermic reaction, heat is absorbed as a reactant. That means overall there is a lot of heat that is needed at the beginning in order to have the reaction occur. And so this means that our overall change in energy is going to be positive. So this little triangle here means change in. The E stands for energy, and the P is obviously positive. So this means that energy is gained. Now, when we look at exothermic, heat is going to be released as a product. And so we can see these are very different, they're opposites of each other. And so this means that our change in energy is negative, which means that energy is lost. Okay, so in one, energy is gained, in another, energy is lost. Now, one way to help you remember what type you're talking about is endo sounds like in, meaning heat is going in, and exo sounds like exit, which means energy is going out. And so that's one way to help you remember. Now, you can recognize these by 2 different graphs. So this first one is the graph of a endothermic reaction. The reason why is we can see on our graph we have energy on our y-axis measured in kilojoules, which we will talk more about later. That's our unit. And then time on the x-axis. So if we talk about time, that means at the very beginning, we're over here in this side. So that means this part here is the energy of our reactants. So ER is our energy of our reactants. And our reactants in this case, we're just going to make up a reaction, is A plus B. So these chemicals, A and B, have reactants that are stored in the bonds. Okay, so let's go ahead and write that down. So energy is stored in the bonds of these reactions. And in fact, it's potential energy. So remember, potential energy is one type of energy, and there's kinetic energy as well. And potential energy is stored in these bonds, meaning there's the potential for some sort of reaction to occur. Now, what happens, as we see, it starts off and it's flat, and then they start to react, and we see that the energy is going up. This means that energy is being absorbed. Okay, so as it's going up, it's being absorbed. And then we see that a little bit of energy is released here. It starts to go down again. Okay, now almost all reactions have some energy absorbed and some energy released, okay, in order to form these products. So C plus D, which in this case, we would measure this amount would be the energy of our products, which I guess I'll go ahead and write out these words for you guys. That would be the energy of our products. But for the overall reaction and how we label, we actually look at the difference between the energy of our products and the energy of our reactants. Now remember, difference means subtraction in math. And so if we look at our reaction, our overall change, which remember the triangle means change in, the energy of our reaction would be the energy of our products minus the energy of our reactants. And so we can see that if we were to subtract a big number minus a little number, we would get a positive number. You can also draw an arrow from your reactants to your products. And since it points up, that means you know that your overall change in energy is going to be positive because it points upwards. And so this is how we know that the overall change in energy is equal to the energy of the products minus the energy of the reactants. Okay, and so this would be an endothermic graph. And you could also see its reaction written like two separate ways. You could have said A plus B plus, heat produces C plus D. Okay, you could have also seen it written as A plus B produces C plus D, and you could have had delta E is equal to, 50 kilojoules kind of written at the end. And because this number is positive, you would know that it's written as a reactant. You could have also just seen if it is 50, which we don't have numbers on our graph, so we can't be for sure. You could have seen it just written as 50 kilojoules in the actual reaction there. And so you'll have questions where you just need to be able to read the graph and kind of explain like what's going on, and maybe do some reading of the numbers to figure out, okay, how much energy is in the products, how much energy is in the reactants, calculating your delta E of reaction. Okay, so just doing some basic subtraction here. Now, the other type of graph is an exothermic graph. And you can already see that it looks like the opposite of this, but remember, with time being on our x-axis, that means that this first part here is still our reactants. So if in this case, let's reverse it, so C plus D, okay, that means from here all the way to here, that's our energy of our reactants. That means they're starting off with a lot of energy. And we can see that they absorb some energy. They absorb just a little bit, but you can see the majority of their energy is released. And so this energy being released will produce our products, A plus B. And we can see that the energy of our products is much lower than the energy of our reactants. And so if we draw that arrow I was telling you guys about earlier from our reactants to our products, it points down, which means our overall change in energy of our reaction is negative, meaning that more of the energy is released than is absorbed. And so it would be that difference there. So again, our delta E of reaction, so the change in energy of the reaction would be equal to the energy of our products minus the energy of our reactants, which I'm just abbreviating as P and R for products and reactants. And so this is, I mean, you read it the exact same way, but you can tell that these graphs are very, very similar, but opposites of each other. So you want to pay attention to which one, does it start high or start low, end high or end low in terms of your graph. So hope you learned something. Take notes.